Right, so welcome everyone to this week's joint algebra seminar. It's my pleasure to welcome Daniel Tubbenhauer, who's going to tell us about SL2 and fractals, or modular representation theory in a toy example. So thanks very much.
Yeah, so first of all, thank you very much for the invitation. It's always a pleasure to come to the UK, only remotely, of course. Actually, the UK was one of the last countries I visited before this whole crisis started. So it's really a pleasure to be here today. Yes, so I want to talk a little bit about a project I got obsessed with about a year ago, and which hopefully at one point will make its own archive or whatever. So how fractal structures arise in modular representation theory, or basically why modular representation theory is a good source of fractals, and modular representation theory in the end is so hard, so much more complicated than classical representation theory, by which I mean, let's say, over the complex numbers, because you kind of having kind of some discrete discrete dynamical system, so fractals will appear everywhere. The only case we really understand right now, so the story is really the same for any reductive group, whatever, but you basically can't prove anything well, not anything, but our knowledge about reductive groups in character, or the representation in characteristic P is really basically SL2, a bit about SL3, and that's about it. But in SL2 I can show you everything very explicitly, and it gets pretty nice. So for example, I will explain what you will see right now, this nice, I don't know really how to call it, like a whatever, teardrop thing, fractal structure. Okay, so let me, so the basic question I would like to answer today, or give you some partial answer, is what I can say about finite dimensional modules representations of SL2. And there are basically three main questions you can address. One of them is reasonably classical, the other ones are more modern questions. So the first thing you would ask is, what can you say basically about the Grothendieck group of the Grothendieck ring of the category? So what can you say about the modules and their structure? Like, can you write down dimension formulas, character formulas, all these questions. A bit more modern, so maybe a question from the 80s or 90s would be, in particular, if you think about quantum groups, then it gets really interesting because you would like to do some kind of knot invariance or whatever. But in principle, there is a Hopf algebra structure, which basically means you can tensor representations, and you would like to answer not just the question, how does the Grothendieck ring looks like as a vector space, like character formulas, but maybe you can say something about its monoidal structure, its tensor product structure, its multiplication. So I would call this fusion roots. And maybe the latest kind of question you would like to ask is in this flavor of categorification. Can you say actually something about the category itself, not just about the objects, but can you say something about the category, which would mean something like morphisms of representations and whatever kind of structure they will satisfy or they have. And it turns out, and this is why I'm here, or what I'm going to tell you, that in characteristic P, all of these questions give rise to fractal structures, to pretty beautiful ones. So here you see two examples, which I'm also going to explain in this talk. So just to be sure, I have some underlying field of characteristic, of some characteristic, could be characteristic 0, but the most interesting thing will be in characteristic P. And to be completely precise, you can already see it here from those pictures. So someone warned me I shouldn't call those these pictures fractals, because they're in some sense inverse fractals. Let me explain. So the classical fractal you might think about, like a Mandelbrot set or whatever, is like when you zoom in, you see everything on a smaller scale. The fractals you see here are inverted. If you zoom out, you see everything on a bigger scale. So, but that's just terminology. So I will just call them fractals. Yes. So in some sense, the modular representation theory is much harder than the classical case. I'll kind of explain both at once. because you always see those fractal structures, you always have some fractal behavior in some way, and the other is very periodic. It's like a line compared to a fractal. It's much easier. A little bit about the terminology before I explain the first fractal, the one here on the right, on the left, of course, is so basically characteristic 0 in this modular representation theory sense is a little bit of a bad terminology. You should really call it characteristic infinity. It's like doing modular representation theory for a very, very, very huge prime. So I will use this philosophy, and for me characteristic infinity is let's say complex numbers, so something over a ground field of characteristic 0. That's unfortunate terminology, but well, whatever. So characteristic 0 is what you usually read in textbooks, and it should be called characteristic infinity, at least in my humble opinion. Anyway, so let me just jump into it with a very classical story. If you haven't seen it, here you go. It's very nice. It's very nice, and it goes back to Hermann Weyl. So by now, it's, as you can see, it's about 100 years old. And what he did is he basically wrote down closed formulas for the simple modules of SL2, and they are nowadays called after him. They're nowadays called Weyl modules, and my notation for them is this delta here, which is kind of the classical notation for those Weyl modules, and they will depend on an input, and the input is basically the dimension, and again there's some mess of terminology, so the crucial number for everything I'm going to explain is V, which is the dimension of the module. For example, delta 5 minus 1 has dimension 5, but the 4 here is referring to what people usually call the highest weight. So for me, the dimension, or V is the interesting number. That's why I'm always going to write V minus 1, just to remind you that V will be the important number, and not the highest weight itself. It's a row shifted version of the highest weight for the experts. Anyway, that doesn't really matter. So V is a crucial number. Don't get confused if I write something like delta 1 minus 1. Right? So just to be sure. So here delta 1 minus 1 is just a trivial one. Anyway, so Weyl's idea basically works as follows. So for each natural number, you have one of those modules, and he writes down a basis, which are just the corresponding, let's say you have polynomials in x and y, and the basis is then just given by the corresponding, homogeneous, so let's say degree, what is this, 3 polynomials in this case. Degree 4 polynomials, degree 5 polynomials, and so on. And he explains that SL2, so here a matrix from SL2, A, B, C, D, satisfying the usual SL2 relation. How does it act actually on this module? You want to write down an action, and it's really just the matrix. You will see an example in a second. So basically, you multiply those polynomials. So here, A, C, B, D. You expand it, and you look at on the appearing coefficients in terms of those basis elements. To be completely explicit here, for example, this is a huge matrix, but just to be sure, we are all on the same page, and that this is nothing fancy. This is really extremely explicit. I certainly haven't calculated this matrix myself. I could have. It's not so hard. But this is some kind of computer algebra program, and it's very easy. So A, B, C, D. So the first and the last row should look familiar because they are just expanding. In this case, AX plus CY to the sixth, and then look for the corresponding appearing basis elements. And the numbers you see here, so ignore A and C. So here's a 1, here's a 6, here's a 15, here's a 20, 15, 6, 1. Should remind, well, these are just the binomial coefficients, of course, because what you do is you expand those expressions in terms of, well, you do the binomial formula, right? And the other rows are kind of mixtures. It's really easy to write down. Don't worry about it too much. The point is you will see binomials turning up all over the place. In a more modern language, so this is how Hermann Weyl did it. In a more modern language, you would probably just call them symmetric powers. the vector representation. They're just symmetric powers of a two-dimensional space. Two-dimensional space is my xy. But anyway, the point is they are binomials. And then Hermann-Weyl went on. So he looked probably at those modules a little bit closer. And for example, if you would take my example above here, and you would be really good in linear algebra, like Hermann-Weyl was really a genius in linear algebra, you could check that this thing here has no common eigensystem in terms of ABCD. And basically this implies that this is an irreducible or a simple module. So irreducible and simple for me is the same. So that's already what he observed, 100 years ago. And if you go to characteristic 2, well, you take this matrix, which obviously is defined integrally, as you can see. So I have a K here, but the matrix itself has only integral entries. So you can specialize it to whatever, a field of characteristic 2, or strictly speaking, it's algebraic closure. And for instance, this 20 would die, right? It will give a 0, here's a 10, and a 10 that dies, and so on. So the whole matrix shrinks, a lot of terms die, and that's what remains. And if you look at it, I mean, now it's really easy. You see in the middle this almost zero, column. And actually, it's very easy to see that there's now a common eigenvector of this module, which just means it's not simple. There's a simple subrepresentation, which sits exactly here in the middle and is the span of this common eigenvector. Okay, so that's what Hermann-Weyl did a long time ago. So you look at those expressions, you basically by definition this will be modules. They're defined integrally. You can reduce them mod p, or you can study them over a field of characteristic infinity, right? Characteristic 0. And in characteristic infinity, nothing dies, and you don't find any common eigensystem. They are simple. And that's exactly what he observed. So when is this module simple? It's simple if and only if the binomials don't vanish, the corresponding binomials for all smaller values. And don't look too much at, well, by the Luca theorem, which I have here, which I will repeat in a second, this basically never happens in characteristic P. So let me explain. And always happens in characteristic 0. So let me explain. So you're only worried about vanishing of binomials, basically because of the explicit form of those modules. So how can you check whether binomials vanish or not? Well, there's a famous theorem. It's called the Luca theorem, and it's really beautiful. So it works as follows. So you wonder about A over B in characteristic P. That's basically what you are questioning, and this is how it works. It's very easy. You write. So this expression here that I'm using here, so this square brackets and then some numbers, that's just a p-adic expansion. The p-adic expansion of the number, so just a0 to the p0, a1 to p times p, a2 times p squared, and so on. And you just write those down, and then, so here for example, and then the binomial in characteristic P is just the product of the binomials over the digits of the p-adic expansion. So just AI over BI, modulo P, which is really good because those numbers are much smaller, of course, because they are p-adic expansions. So the numbers AI are always lower than P. So you can compute those binomials very easily, and you basically immediately observe that this has no chance to be non-zero except V is a prime power. And this here is just saying V is a prime power because everything else is 0, and then I have an AR times P to the R. Okay, so in characteristic P, basically Hermann-Weyl already showed that those modules are simple if and only if the dimension is a prime power, which of course almost never happens. Let me comment on characteristic infinity in a second. So in characteristic infinity, you can think of those p-adic expansions as just the usual numbers. Why? Because A0 is now allowed to be, well, it's allowed to be lower than P, but P is infinite. So any number is just its own periodic extension for P equals infinity. So V is always a prime power in that sense, and all the delta modules are simple. Right? So the difference between, so the smaller the prime, the longer those expressions get, and the more likely it is that this guy is not simple. That's basically what Hermann-Weyl showed a while ago. And this is basically the answer when are those modules simple, and he also showed that these are all finite dimensional simple modules. So in characteristic 0, the delta modules form a complete non-redundant set of finite dimensional simple modules. And in characteristic P, those simple submodules that you find, so those ones here, then form a complete list of non-irreducible. Well, or the other way around. There's a submodule and there's a head of the module, which is the biggest subquotient. I will show it to you explicitly in another example. And the biggest subquotient is, you take that as your replacement for delta, and we'll call them L in a second. And then those form a complete list of non-redundant list of simple modules, finite dimensional ones. And all because basically of some vanishing of binomials. And if you know the story of vanishing of binomials, then the following is maybe not far-fetched. So you write down the same table, and it already looks like the start. I mean, these are symmetric powers. So this is, of course, just the start of some kind of Pascal's triangle. And here in this whatever purple-like color, these are the simples. So up to a certain point, this is characteristic 5. No binomial can vanish because the binomials are just too small to vanish. They're never divisible by 5. So the delta module is the simple module, but at one point they will break down, right? So this one, for example, the delta 6 minus 1 has a submodule here at the extreme points. I will make it even more explicit in a second, so give me a second. Delta 7 1 has a submodule here in the, two neighboring extreme points, whatever you want to call it. And in this case here, this is a submodule in the middle, and the purple one is a quotient. Okay. For example, 7 1 has the L7 1, 7 minus 1, as its quotient, the purple one, and in this case we can just see it by just shifting it up here. So here you go. So the L3 minus 1 as its factors. And well, if you continue this all the way down, because it's vanishing of binomials, and you know this theorem, so Luca Theorem, the simples arrange themselves in Pascal's triangle modulo prime. So this little white box up here, and now the colors are really bad, so this really white box up here is this purple triangle here, and here it starts to break, so the black part here is also the black part. So this on this line the simple is just, well, the two vertices here. On this line again the simple is just the two vertices. On this huge line, which is the next one here, which I haven't explained anymore, which I haven't illustrated anymore, the simple will be again just supported in the two outer vertices, and you get this fractal pattern, which is just Pascal's triangle modular prime. Right. So in characteristic infinity, where this little triangle will be everything, you just get Pascal's triangle, and these are your characters of the simple modules. And in characteristic whatever P, you get those fractal patterns. And I mean, it really is this, I zoom out and I see the same thing turning up on a bigger scale, right? This little triangle up here is just scaled by 5 in this case, so by P in this next bigger triangle, and so forth and so forth. I mean, this is pretty amazing and very nice, and goes back to Hermann-Weyl. And I learned this, well, way too late. I should have known this from the very start, but whatever, something like 2 years ago, and this is only my fault because, as I said, it's super well known. But anyway, so this was kind of the starting point of the project I want to explain today, because, well, okay, if the simple modules have some nice fractal patterns, maybe you can hope that other things also have nice fractal patterns. And so we moved on and looked. So this was the story about simples. Let me just wrap it up. Let me just rephrase it and say it once more. The simples arrange themselves in Pascal's triangle modulo P. Basically because certain binomials vanish. Okay, so the next thing you might try is, okay, if the simples, the irreducibles are certainly the first class of modules you would try, but there might be other classes of modules. So if you're familiar with, let's say, finite dimensional algebras, maybe the next thing you would try are projective indeposables. Sadly, for SL2 and for any reductive group in characteristic P, all projectives are infinite dimensional and they're not really nice and not really well behaved. But there's a replacement type of module which I won't define because they're a little bit tricky to define, and they were found much later than simple modules or projective modules because they're a little bit tricky to define. But they basically play the role of a replacement for projective modules. So you don't have projective modules, or at least no finite dimensional ones, but you have those modules which are called tilting modules. And I denote them by T, same indexing set, and the indecomposables, like in classical, whatever, finite dimension theory of finite dimensional algebras, the simples and the indecomposable projectives are in a bijection, so they have the same parametrizing set, and it's the same here. It's indecomposable tilting modules, this is my notation T, and the simple modules have the same underlying parametrizing set, which is just the natural numbers. However, in this case, V is not quite the dimension. These modules get a bit bigger. And I will explain in a second how they look like, instead of defining them for you. So basically, for the experts, they're defined using filtrations of those delta modules and the duals of the delta modules. I will show you the duals in a second. Just to be on the same page, in the classical case, so if you would do representation theory of finite dimensional algebras in a semi-simple case, then projectives and simples, projective indecomposables and simples coincide, and it's the same here. So in the semi-simple case, so characteristics, actually any field of characteristics 0, the tilting module is the simple module, is the delta module, is the dual delta module. And the dual delta module, let me just say it, it's exactly the same as I've done, but now you take transpose matrix instead of the one I showed you. And in characteristic 0, you can show that they are still equivalent, although you take transpose matrix. In characteristic P in general, they just have the same character. They're not equivalent as modules anymore. So there's a slight distinction between the delta and the nabla modules. Anyway, so tilting modules, that's how you should think about them. They play a replacement of projective modules for those reductive groups, here for SL2, for example. And the name comes from the fact that they really have this, whatever, diamond-like shape. So they always have a delta of the corresponding dimension or highest weight sitting at the top, and they always have a nabla of the corresponding dimension or highest weight sitting at the bottom, and some multiplicities we would like to compute. So here, whatever, some other deltas, some other nablas. But they have this nice tilting symmetry. So if you tilt your head, then it still looks the same, right? So if you would now tilt your head, I can't do it, but if you would tilt a picture, whatever, 180 degrees, or mirror it along the axis, then it would still look the same. So they have some nice properties. In particular, they are self-dual in a reasonable sense. Anyway, so if you know those modules, and you know that they form a nice class of modules, like projective indecomposables, you would ask for what are their characters. A slightly different question, but basically you can answer this question because the delta modules are so easy. They're still given by, so they're defined integral and always given by Pascal's triangle. They're easy to write down, their characters, their dimensions, everything is known about them. So in order to answer the question, what are the tilting characters, the characters of the tilting modules, it suffices to count how many of the deltas or equivalently how many of the nublars appear in the delta mod in the tilting module. I will come back to this in a second, but let me give you an example of a tilting module before. So so this is, for example, how a tilting module looks like in characteristic 3. So it really just, so this is just a Weil module here, right, the 4-dimensional one, and generically it would just be, let's say, the classical generators of the Lie group, and this with the Lie algebra, and this is in this case completely equivalent, would act by 1, 2, and 3, or 1, 2, and 3 in the other direction. So the E and F generators of the corresponding Lie group. And 3 is already bad in characteristic P, in characteristic 3, of course. So those arrows are actually 0, and you can see here the submodule, and you can see here the quotient. On the flip side, you also have the delta module, which in the tilting module, which is in this case more like a circle, sits at the bottom. It looks exactly the same, but the arrows are in the opposite direction. In particular, this now is a quotient, and this guy is a submodule. Okay? And tilting modules are basically glued together using those delta modules, such that they become indecomposable. Right? So let me say it again. So here is the delta module. It's a nice circle. Here is the nublar module. And the only difference between delta and nublar is the reversion of the arrows. And in characteristic 3, the red arrows are 0. So you see here a submodule and here a quotient for the delta module, and for the nublar module it's vice versa. And tilting modules, again, is a kind of this tilting symmetry. You tilt your hat and they look exactly the same. Okay, so let me just move on. So so basically I want to answer the question, what are the characters of the tilting modules equivalently, or not quite equivalently, but what I want to know is how often the delta appears in the tilting module, because then I could write down the tilting characters. It's not quite a closed formula, but it's close to be a closed formula. So I'm interested in the Weil factors, in the delta factors of my tilting modules. And this is how it works. It's actually quite easy. It's some combinatorics, not very hard, very easy, and the only thing you need to know is, well, the one I care about is V and its periodic extension. Again, this is A0 plus A1 times P plus A2 times P squared, and so on. So what are the Weil factors of T V minus 1? Okay. They are given by what I call the negative digit game. It works as follows. You write down, here's a huge example in characteristic 11. So this is probably the biggest number I ever wrote on any slide. But anyway, so if you extend this number periodically, and that's what I ask you to do, is then it will be this, 140771. Okay, I hope I did my calculation correct. So it's a easy problem, right? Just express it periodically. And the appearing Weil factors are now all the sign swaps in front of those, well, you can swap the sign with 0, that's boring, in front of the non-zero numbers, non-zero digits. So in this case you get 2 times 2 times 2 times 2 is 8 Weil factors. Okay? It has 8 Weil factors. In particular it's huge, by the way, right? So each Weil factor has a corresponding dimension, so this guy is huge. It has 8 Weil factors, and they're just given by flipping digits around. Like this one, 1, 4, so plus 0, minus 7, minus 7, minus 1, and I just interpret those numbers as periodic extensions. So minus 1, minus 7 times b, minus 7 times b squared, well, 0, 4 times p to the 4th, I think now, and so on. It's really explicit, it's extremely easy. Just flipping some digits, the signs of some digits in the periodic extension. It's really easy, which is very surprising if you think of, well, I haven't told you, but they have a pretty complicated definition, the tilting modules. The projectives, so this basically nails down, if you want, the projectives of SL2. And yeah, and then you just, think, okay, let's write down a matrix. Let's write down a matrix, so those are those multiplicities I wanted to count. Let's just write down a matrix. So tilting modules are along the columns, and while modules are along the rows. So whenever you have the tilting module for this number here, which I hope is something like 81, because this is characteristic 3, right? It looks good. Has those while factors turning up. So here's one, 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 8 in total. And you get this really beautiful, like, again, the fractal pattern just by counting the. So these are basically, as I said, the characters of the tilting modules. The characters of the tilting modules are this, whatever it is, like a fractal waterfall thing. I don't know. So the characters of the simple modules, Pascal's triangle, mod P, and the characters of the tilting modules are those fractal waterfall-like structures. And you can see it here again. So 1, 2, 3, and it has some kind of lag going out. 1, 2, 3, another lag, and now comes the first prime power, and it gets a longer lag of length 9. At the next prime power, this is roughly here, it's 27. It gets another lag of length 27. At 81, it gets another lag, and so on. So the next one would be somewhere down here. And I don't know how you feel, but I think that's a pretty nice answer for this question. Like, write down the characters of the projective modules. Here you go. It's basically a negative digit game on the periodic extension, and you again get some fractal patterns. So let me summarize what we have seen so far. So basically, I addressed the first of my questions I wanted to ask. So what can you say about the modules? There are not many other interesting modules, finite dimensional ones, except the tilting modules and the simple modules. So in some sense, this is done. You can ask other questions, of course, now, like the delta modules, the deltas in the simples, the simples in the deltas, for example, not just the top simples, and you get similar pictures like this one. You can always get some fractal structure, and you can always get some game, some combinatorial game you play on the digits of the periodic extension. Okay, so if you know this, and I was really happy when I learned it, you might want to push on. You might hope for even more fractals. But let's go to some multiplication structure of those modules, right? SL2 is a Hopf algebra, so it has coproduct, so I can multiply representations. So why not? In other words, the Grothendieck ring of my representation category, the Grothendieck group of my representation category is a ring. So this was the right way to say it. So you can multiply representations. So the question you would like to ask is, can you kind of write down the structure constants of the Grothendieck ring? It turns out that is not so easy in general. So the multiplicative structure in the category itself is a bit ill-behaved. But tilting modules, so I will stay with those tilting modules, because they form this funny subcategory where tilting times tilting stays tilting. All the other modules, whatever, the delta modules, the while modules, or the simple modules, never form really a monoidal subcategory. You always kind of run out of your. So you go somewhere else, you see some crazy indecomposable summons turning up. It's not really well behaved. Tilting times tilting is a really nice monoidal category, and people like it. It turns up, the semi-simplification turns up in physics and so on, so like fusion rings and so on. And that's where the name actually comes from. So the fusion rules are basically, so I have my tilting module, and I know that, this should be a V, I'm sorry. V and W. So TV and TW. And I know that the result will be a tilting module, so there will be some decomposition in some indecomposable tilting modules. And you would write down the structure constants of this question. And another question you would like to ask, and I will explain how this works, and you again see a fractal. And the other question you would like to ask is, for example, my Grothendieck, group is an algebra or a ring, whatever, and so you can ask for what are the ideals in this algebra, And the terminology people usually use here is they call these thick tensor ideals. These are just ideals in the Grothendieck ring. So you only care about, well, there are also ideals in the categorical sense, but you can define them just using a set of objects. So basically, it's a decategorified structure. Two natural questions you would like to answer. You have a multiplicative structure. You just said something about the vector space structure, basically, of the Grothendieck ring, of the Grothendieck algebra, whatever. So now, why not look at the multiplicative structure? Maybe that's also given by some fractals. Maybe you will see fractals nobody has seen before. And yes, we will, so it will be very nice. Well, I'm not sure whether nobody has seen them before, but it will be very nice. So let me answer those two questions. Right? Remember, I only want to write down basically the structure constants of the Grothendieck ring and ideals or whatever. Okay. The answer is given in what physicists call a fusion graph. So that's really a graph. And how does it work? Okay. It works as follows. So I have a graph, and the vertices of my graph are just the indecomposable objects of my category. Okay? So in my case, the objects, you can identify them with the tilting modules, because they are the indecomposable objects in my category. And you write an edge between two vertices if one of them appears in the tensor product. Okay? So let me say it again. So because I kind of screwed it up, you fix one tilting module and you wonder for its fusion graph. And it's basically how it acts on the Grothendieck ring, right? You tensor everything with the corresponding tilting module, or indecomposable, in this case TV minus 1, and you look what kind of summons appear, and you draw edges according to the summons. I give you a very explicit example in a second, so don't worry. But it's a combinatorial datum. It's a graph you associate to the multiplication, to the monoidal structure in your category. And this is a classical trick. So for any reasonable additive, whatever, blah, monoidal category, this actually works, and physicists call it, or fusion graphs. So let me give you a baby example, such that we are all on the same page. So not related to tilting modules, just to make sure we understand how those fusion graphs work. So assume I have two indecomposable objects in my category, 1 and x. Okay? And 1 is the identity, so it acts as identity. And x satisfies this multiplication rule. If you square it, you see 1 plus x. Okay, that's kind of the easiest example you can imagine. And then you could write down two fusion graphs, one for the object 1 and one for the object x, and they will look as follows. So you write down one vertex for each indecomposable. So I have two vertices, 2, 1, 2, and then you write an arrow if you act with one, you see the other one as a summand. Okay, so this of course is just the identity matrix. So if you would write down this is a matrix with identity matrix. So 1 times 1 is 1, so you write a loop from 1 to 1. 1 times x is x, so you write a loop from x to x. Okay. This one is a little bit more exciting. And if you understand this one, then you have understood fusion graphs basically. So you have two vertices corresponding to my indecomposable objects. And well, let's see, x times 1 is x. So you draw an arrow from 1 to x. Okay. X times x, well, I told you what x times x is. It's 1 plus x. So I draw two arrows, one from x to 1 and one from x to itself. Okay. I'll say it again. X times x is 1 plus x. So I draw one arrow from x to 1 and from x to itself. And this is a game you can play with, as I said, any reasonable monoidal category, in particular with my tilting modules. And this is what I want to do. So I want to write down an infinite graph, because my indecomposables are indexed by natural numbers. And I want to see how certain tilting modules act on this category, and I want to write down the corresponding graph. And the first thing you would write down is, well, let's go back. The while module, this is just the vector representation. It's a two-dimensional space, and SL2 acts as, well, SL2 matrices act as matrices, so this is called the vector representation. And it turns out that this module is always the tilting module, so the delta is the tilting, is the simple, everything is fine. So the vector representation is kind of the nicest possible module you can imagine, which is not completely trivial. So the first thing you would ask is, go on. Too fancy. The first thing you would ask is, can you write down the fusion graph of the vector representation? So tensoring was the generator of the category, right? It actually is the generator of the category. So any indecomposable module will be a summand of a big enough tensor product of vector representations. So it's like you have an algebra and it has some generator, and the first thing you would ask is, can I write down the structure constants for multiplying with this generator? At least that's the first question I would ask. And it turns out that the answer is very nice. So I have 2 videos for you, but they don't play in presentation mode, so I have to leave presentation mode for a second. Let me zoom in. Okay, so the fusion graph, here you go. The fusion graph for characteristic infinity, right? P equals infinity. I tensor with the vector representation. And this is the first star. So first 4 vertices. So here is T1 minus 1, T2 minus 1, T3 minus 1, T4 minus 1. And I will add a few in a second. And this is how it works. So the classical kind of Clebsch-Gordon rule, if you know it, will tell you this works as follows. If you tensor anything with this module, you go 1 down and you go 1 up. So remember this is T2 minus 1. So T1 tensor T1 is this one plus this one. T2 tensor T1 is this one plus this one. T4 tensor T1 is this one plus this one. So you get this line graph. Well, it will be a circle in a second. This graph where at each point you just have one edge to the left and one edge to the right. And this is how it looks like, right? It's not very exciting. It's not a fractal. It's p equals infinity, of course. It just you will see in a second why I like to illustrate it on a circle. But it's basically an infinite line, and it's not very exciting. Okay, good. That's it. Okay, so the fusion graph for tensoring with a vector representation is, well, let's say a circle. Okay, so let's do the same trick in characteristic 2, and any characteristic works the same, but interesting things happen at prime powers, so I take the smallest possible prime to have a short video, but you will be able to imagine how it works for any prime. So it starts off a little bit weirdish already, so this is the same case. So because there are some missing edges. Okay? So from 2, you can't go back anymore, you only go up. So T1 tensor T1 is actually the indecomposable T2 in this case. T3 is then again the usual one, and the next one will be bad, the next one will be good, the next one will be bad. So you always have a missing edge at each second step. In contrast to here, where everything was, oh, this is not good. In contrast to the above, where everything was working pretty well. So you have this periodicity, missing, and then usual, missing, usual, and so on. If that would be everything, I wouldn't talk about fractals, because that is not a fractal, that's periodic, right? So it gets better. So the same pattern, I will play the video several times, so don't worry. The same pattern will repeat on bigger scale, and that's exactly the fractal. So here comes the next longer edge, next one. Let me just play it once and I will play it again, next one. So you basically can't see the small edges anymore, but at each prime power you will get one of those longer edges. The next prime power is something like 62, here you go. So or prime power plus 1, whatever. So from this one you can jump down, and you don't have a missing edge here, but anyway, let me play it again. So it's always the same pattern, no edge, double edge, no edge, double edge. It's the same pattern. There's a missing edge every time, and then there comes the next edge. And at every prime power it gets longer and longer and longer. The next prime power, here you go. We play it once more. So longer edge, and that's why I would like to illustrate it on the circle, because those long edges, for the obvious reason. So here you go. There's another longer one, and it's the next prime power. It jumps again. Very good. And it goes on and on. So this is just exactly the same as on the small scale, but now you go basically from the prime power to half of the prime power. So it's a really long edge. And yeah, so if you tensor this module with T1, which looks like T1 is two-dimensional, like you can't go away very far, but you jump down by a lot. Okay, let me go back to presentation. Okay, so this is the story for the fusion graph. So the fusion graph is this funny fractal-like circle with longer and longer edges, and they always jump p units, 1 unit, p units, p squared units, p cubed units, and they repeat in the same frame after one step, after p steps, after p squared steps, and so on. So it's a pattern inside of a pattern. So that's why I call it a fractal. So it's actually a fractal graph in the sense of graph theory. So people in graph theory have looked at fractal graphs. Okay, so we haven't looked at other structure constants yet, but this is kind of work in progress, and I already have some pictures, which I'm not going to show you. And yes, you get fractal structures as well, of course. Not as easy as this one, because this is kind of the easiest case you could have imagined, but kind of the same flavor. Another question which I would like to answer, and this again has a very nice answer, is what are actually the ideals in my Grothendieck ring? I just showed you, well, let me just show you the answer. I just showed you this picture. So this, so in this case, this is p equals 3. It's the same pattern. You have the longer edges, and everything repeats on a scale that gets bigger and bigger. So there will be the next longer edge, and the next prime point will be another long edge, and so on. And what you observe here is that. So here you always have this missing edge that you also that I showed you in the p equals 2 case. Here's a missing edge, so it only goes in one direction. In particular, as soon as you jump into this part, which I indicate by this black arrow, you can't jump out anymore. So as soon as you're here on this part of the graph, you can't go back. Same here, as soon as you're here, you can't go back anymore, because there's a missing edge backwards. And the long edges arrange themselves in a perfect way, so it doesn't jump to here. This would be bad. No, it jumps to the right spot, so you really can't go back anymore. And at each prime power, you have the same pattern because it's a fractal, it repeats itself, and so on. So at each prime power, so here's 9, here's 27, here's 3, and this is characteristic 3. You have the start of a strongly connected component of this graph. So strongly connected is just connected in the oriented sense. So I can't go back anymore. And it's not hard to see because this was the graph for T1. It's not hard to see that these are exactly the ideals in your category. So the trivial ideal is just everything, okay? It starts at p to the 0. What a surprise! So it's a unit of my ring. And the next ideal starts at 3, so p. The next ideal starts at p squared. The next ideal starts at p. This is p cubed, and so on. So the tensor ideals. You need one extra argument to show that these are all tensor ideals, but this is not so hard. These are really all. So the tensor ideals form this nice chain of nested ideals. The trivial one, one indexed by p, one indexed by p squared, one indexed and so on. And it turns out that as categories they are all isomorphic, which is kind of fun because it's a fractal. Like the structure of the category is again repeated. It's in a shifted version, in a p-shifted version of itself. So although they look like they are smaller because they're nested, they're not really smaller because we're dealing with infinite things and everything is just shifted by p basically. Okay, so the tensor ideals also arrange themselves in some kind of fractal pattern, a very easy one. P squared, p whatever. And now we can take the quotient by those ideals, like you can just take a quotient of ring by an ideal, and you get what people call the Valinde category, or the Valinde categories. It's just corresponding to some prime power. It's just tilting modulo the corresponding ideal, And it turns out that this category actually has projective modules, and it has enough projective modules. And then you would ask, well, okay, can I write down the Cartan matrix of this category, which is how often the corresponding simple appear in the projectives. And, well, I haven't written down a formula, but it's basically given very similar to the one I showed you to the negative digit game, if you remember. And this is the answer. So projectives are along the columns. Simples are along the rows, and whatever. When you're here, you have projective, which is simple, which is not simple. It has a lot of other factors turning up. So when you're here, you can just see all the simples by corresponding slicing. Yeah, and I'm a little bit skeptical right now whether I got my rows and columns correct, but in this case it doesn't matter because it's a symmetric matrix. So one is correct. So this is the number of simples in the projectives. There are colors. So in contrast to the tilting characters, there will be multiplicities, and those colors indicate multiplicities, and also the colors. So the multiplicities satisfy some fractal pattern. So the fractal pattern you should see here is this arrow-like structure, and it's an arrow, so it's characteristic 3, and two bigger arrows. Here's the start of, well, here will be a next one of those arrows, and each one of those arrows has little arrows everywhere, and yeah, I don't know, like an arrow-like fractal. So this was certainly a fractal I haven't expected, and I'm not sure whether anyone has seen this before, but it really just comes out by taking those quotient by those ideals, and then ask the natural questions like, can I write down the projective characters in this category? Okay. Very nice answer again. So I basically let me summarize. So in the second part, I basically studied the multiplicative structure of the category. And surprise, surprise, I still get fractals like this funny circle-like graph, which those repeating edges, and this arrow-like structure. I really don't know how to call it. This arrow in the arrow in the arrow. Like in the Cartan matrix of the corresponding quotients if you write down the cell ideals. As I said, you can ask other questions in that direction, which we haven't answered yet, but computer calculations support that you again get fractal patterns which I haven't seen before. And let me also say that you can ask the same questions for SL3 or whatever, and you can do computer calculations and you get higher versions of those, so multi-dimensional versions. All of this is here kind of flat in the plane, and you would get multi-dimensional versions. There's just no way to prove it. We're already struggling to prove this nonsense here. And this is just SL2. Anyway, I promised you one last section. I still have something like 6 minutes to go, maybe 7 because we started 1 minute late. Basically, I want to tell you that it doesn't stop here. The whole category has fractals everywhere. So there are also fractals on the morphism level. So far, I only told you about kind of the classical questions you would like to answer. Characters and so on. But in some sense, category theory tells you what you should really study morphisms and not objects. And that's what I'm going to explain it next. So what we did is, so here you have another fractal. I will explain this in a second. This is my favorite rainbow, it's another fractal. So basically the first question you would ask is, can you find an easy algebra, let's say a quiver, such that, again, tilting modules is the right category to study. It's just much more well behaved than everything else, such that tilt is equivalent to modules, projective modules over that algebra. In my notation, this is the ZP. Yeah, so it's I want to find a quiver, as I said, such that tilting modules is equivalent as a category to ZP modules, and I'm going to explain how the quiver looks like now. I probably don't have time to go into the proofs, but if you know some kind of diagrammatic algebra, Temperley-Lieb calculus, that's what you would use. And yes, the Temperley-Lieb calculus, the characteristic P, also gets fractal. I don't have time to explain it, but just if you know temporal and deep algebras, they also get fractal in characteristic B. Anyway, so let me explain the quiver. So question is, I hope, clear. I want to find an algebra as easy as possible, a quiver with some relations, such that tilting modules are equivalent to projective modules over this quiver, and indecomposable tiltings are sent to indecomposable projectives. Again, because tiltings are like projectives, so if you have some random algebra, they should correspond to indecomposable projectives. Okay, and the answer is as follows. So all the relations are also fractal, and I will explain them in kind of the first generations, which just means up to certain prime powers. But so it works as follows. So you just list all the vertices, okay? You write down your V, here you go. Each one corresponds to a T, okay? And each T has a certain number of delta factors. So 52 has whatever, 48, 52, 48, 40, 36, 16, 12, 4, and 0. And you draw an edge basically to all of them. This is how it works, and everything gets fractal. You see those longer getting edges because you jump down. Remember that this is given by the multiplicities, that's what I'm using here. They are given by this negative digit game. So the longer your expression actually gets, if you flip one of the top digits, you go down quite a long, quite a big step. So those edges get longer and longer and longer, and they repeat in a certain pattern, like those rainbow things. The colors, in this case, they correspond to certain relations, which are also fractal, which I don't have time to explain, but also the colors repeat and everything. Yeah, so this is the answer. Let me just explain rigorously how this looks like in up to certain prime powers. And then it's the same pattern again, repeated, just like scaled by P and stacked into itself. Okay, the easy case, right? So which is called generation 0. So I go from P to the 0 to basically P minus 1. So I should have written P minus 1 here. So everything where we can't divide by P, then the quiver is very boring. You see it here. This is characteristic 3, so this is my cutoff point here, and the quiver just has 3 vertices and no edges, not very exciting. And if you continue this periodically, so just 3 vertices, then 3 vertices, 3 vertices, and so on, and no edges at all, so the most easiest algebra you can imagine, just a quiver just given by vertices, so it's just a copy of your ground field several times. Then you get it's semi-simple. Then you get the semi-simple case, characteristic infinity. So this question is very silly in the semi-simple case, because if both sides are semi-simple, then of course you just count the number of simple objects. So you just get a certain a quiver that is not even connected. So just each vertex corresponds to a simple module. We already know the parameterization of simple modules. Right, this quiver has to be boring. So let me just do the next example. So you go up to P squared. This is generation 1. And what you will see is basically a lot of those line-like quivers. And you have 2 operators, which are the flipping operators on the digits. I call them up and down. So you either flip digits up or you flip digits down. I haven't explained the up operation, but the down operation was the sign operation. And they satisfy certain relations which are not so hard to write down, like if you go 2 steps, it's 0 in either direction, and each loop at each vertex, so you can go down up or up down, is the same. And this algebra is sometimes called the zigzag algebra. So this is the quiver. Up to a certain point, this is the quiver. And this structure then repeats, that's why it gets fractal. This structure repeats, let's say, if you go to P cubed, so next generation, you have zigzag algebras just nested inside of each other. So you have operators on the 0th digit, you have operators on the first digit, and relations are the relations I showed you along the rows and columns, and squares commute. So whenever you run around the square, it's squares commute. So any possible, up to certain scalars, any possible square commuting relation. And then this just repeats. If you have p to the fourth, you have another line, it gets three-dimensional, you have this cube, so you have this cube-like picture in each direction. It's a zigzag algebra. You have another operator on the second digit now, and you have faces commute-like relations. Anyway, I think I'm out of time, so there's more to say. So you can say something about how does a monoidal structure is reflected on the categories. So this is just as a category, not as a monoidal category. Can you do something as a category? Yes, you can. And you get, again, fractal structures and so on and so on. But sadly, time's up. So thank you very much. And
okay, let's thank the speaker, either by emoji or